Okay, so last class we have covered up to cells, right? So then we have to discuss about some special circuits. Okay, so already Wheatstone bridge you know already, right? So balanced Wheatstone bridge and Wheatstone bridge type of problems you can do already. Then we are going into uh, meter bridge. Meter bridge is an application. Let us take meter bridge. Meter bridge. Meter bridge application of application of balanced balanced Wheatstone bridge. Balanced Wheatstone bridge circuit. Okay, this is the application of balanced Wheatstone bridge circuit. And what is meter bridge? So there will be a wire. There is a wire of 1 meter, and there is a scale here kept. There is a scale kept, meter scale. So it will have reading 0, then 1, 2, 3, 4, like that, up to 100 centimeters. Okay, so markings are there on this. So a meter scale is kept, and then this end of this wire A and B are connected with a battery. Okay, then what happens? Then this side, a unknown resistance, or let us say, yeah, this is unknown, let us say, and this side another known resistance is connected, R2, and in between this we connect a galvanometer, and that galvanometer int, which is called J or jockey, this is moving over the wire. Okay, so this is a simple arrangement. In the textbooks they have complicated, in NCERT if you see the diagram itself is difficult to understand. They are not presenting clearly. So the idea is that two resistances are there. One of them is known, another is unknown. Let us say that this is known resistance. You know its value, known resistance or standard resistance. Standard resistance. Standard means you know this value. This is unknown resistance. Unknown resistance. And you want to find out resistance of the unknown resistance. What is the value of the unknown resistance? So meter bridge circuit is a topic of practical physics. Okay, so there are complicated diagrams, we are not going into that, but a simple diagram we are taking. Okay, in practical physics they have complicated diagram, in the laboratory you have to make, because actual circuit all those things will come. Okay, but here this is a simple diagram. So what you need to do is you need to know that this galvanometer is connected with this end, which is the pointer, and this is called jockey. It can move over this wire. So as you move over this wire, there will be some current in the galvanometer branch, middle branch. So if there is a deflection, that means some current is passing through it. But if there is no deflection, means there is no current passing through it. Okay, so when current in the galvanometer is 0, when no current in galvanometer, no current in galvanometer, it is called null deflection. Null deflection. Deflection. Null deflection means no current in the middle branch. Okay, so when no current happens in the middle branch means what? This point is the point J, this is the point, let us take this point as C. Okay, so no current in the middle branch means here you need to note that this portion of the wire, up to J, behaves like a resistance, and that portion of the wire, this side, it behaves like also as some resistance. Okay, so let us say that this resistance of this portion AG, resistance is resistivity into length. So when null deflection happen, this length is, let us say, x centimeter, and the remaining length is 100 minus x centimeter. Okay, so resistivity into length by area of cross section is same. Note that they have same cross section area because it is a uniform wire. Okay, so resistivity length by area. Similarly, resistance of this portion JB, J to B, is resistivity length is 100 minus x by the area A. Okay, so this is what is happening. And when it is balanced Wheatstone bridge, because balanced Wheatstone bridge means no current flows in the middle branch. So balanced means this ratio of R1 R2 is equal to these two resistance ratios. You know that, right? So in null deflection, in null deflection, in null deflection, it is a balanced Wheatstone bridge. It is a balanced Wheatstone bridge. And if it is a balanced Wheatstone bridge, we can apply the condition for balanced. So resistance R1 by R2 is equal to resistance of AJ by resistance of JB. Now this resistance already you have calculated, and its ratio you can take. This will come as x by 100 minus x. So resistance of R1 by R2 is equal to x by 100 minus x. So you wanted to calculate R1, so R1 becomes R2 into x by 100 minus x. This is how we will calculate. This is how we calculate the unknown resistance. Here, note that the value of x will be measured from the experiment. This x is called null deflection length. X is called null deflection length. Null deflection length. So we'll use this formula to calculate. Clear? Like this. Clear? Done? Okay, so this is what is Wheatstone bridge. That's all. That's all. Now, in some cases, they may ask some modification. Suppose they say that the wire is non-uniform wire radius is changing. Then in that case, how to do that? So suppose if this is a wire and the radius is changing like this. Okay, radius is changing. Suppose here this point is A, this point is B. Let us say that here the radius is R1. Here the wire radius is R2. Okay, this is the axis of this wire, and the length and the length L. L is the length of this. Again, you do the same thing. You are going to connect it with a battery, and here there will be a scale. Some scale you will be keeping it here. 0 centimeter, 100 centimeter. So there will be marking on this, and you will be connecting this side with the resistance R1. Here you will connect this side with R2, and in between you will connect with a galvanometer, where the jockey will be moving over this wire. Again, the same thing will happen. You need to consider this portion of this wire, and you need to also consider that portion of the wire. Okay. So now the thing is that how do you calculate resistance of AJ and how do you calculate resistance of JB? That you need to think of. So first of all, you should know that here the radius is linearly changing. Why? Because it's a straight line slope. Slope is straight. Okay. So suppose if you take this wire like this, and let us say its radius is R1 here and radius is R2 here. So length is L and resistivity is rho. Then what is the resistance of this wire? First of all, you should know the formula for resistance of this wire, whose radius are different. Do you know that? Otherwise, you need to derive it. Okay. Derivation I will do separately. Okay. Let us do the derivation first. So suppose if there is a wire like this, length is L, this is the axis of the wire, and we want to find its resistance. Same material, resistivity is rho. So its resistance here, radius is, let us say, R1, here radius is R2, and total length is L. Suppose I take a small element, small element I take. So at a distance of x I am taking, and its thickness is dx. Okay, thickness means you can see the thickness means here the thickness at the axis is dx. So this will be like almost like a uniform wire. You can take this element. This element is almost like a uniform wire. This resistance you can now write small resistance dr, resistivity into length is dx by area. This area you have to calculate. Let us say that this length is y, this radius is y, so its area will be pi y square, right? Resistivity into length by area, pi y square. That's the formula for resistance. Now I want to integrate, because it is made up of so many small elements and they are all in series. Series means you will simply add them. Add them means integrate them. So total resistance of this will come as integration of dr. Integration will be integration of resistivity, this length dx by pi y square. So how do we get the relation between, because x is changing, y is also changing. So with respect to x we are doing integration, y y you need to write in terms of x. How do we write it? So if you see here, what is x and what is y? X is the change along x-axis, y is the change along y-axis. So if you take a small element which you are taking here, the slope, so this is the change along x-axis and this is the change along y-axis, and you can take that the slope theta will be constant because you draw here or here, anywhere this angle theta will remain constant, right? This angle theta will remain constant. So that dy by dx is tan theta. From here you can understand dy by dx is tan theta, and this tan theta we can calculate because if I extend this one, it will become like a right. We can calculate that. So you cannot, if you don't want, you may think like a simple way, right? Like change in y by change in x. Change in y by changing x also you can say. Suppose when you go from r1 to r2 radius, what is the change here? This is the change in radius and this is the change along length. So this is nothing but L. This is nothing but L, and this is the change in radius, which is r2 minus r1. So this tan theta can also be written as r2 minus r1 by L, okay, which is a constant. R2 minus R1, because in this triangle the R2 minus R1 by length, okay. So how do we do that integration? We can either convert x into y or y into x. So from here we can better convert in terms of y because y square is in denominator. Dx, let us convert into dx, we can convert. So from this dx can be written as dy by tan theta, correct? Dy by tan theta we can write very easily, and then you change that. So this resistance is resistivity. Dx has become dy by tan theta, and this is pi y square. Now everything constant will come out. Resistivity pi tan theta comes out. You have to only integrate dy by y square. Okay, and y is the radius. So radius is changing from r1 to r2. You know the limits also. So r1 to r2 limit also you know. Now you can integrate. Then tan theta we will substitute. Tan theta afterwards we will substitute. It is r2 minus r1 by L. We can do substitution. Okay. So now let us do this calculation. 1 by y square integration you know, right? What is the integration of 1 by y square? So rho pi tan theta. Integration of 1 by y square is minus 1 by y. Y is going from r1 to r2. Let us solve this. So resistivity pi tan theta, you put minus 1 by r2 minus minus plus 1 by r1. Now you tan theta you can substitute because this is the value of tan theta. This is what is tan theta. So tan theta now you substitute. So rho pi tan theta is r2 minus r1 by length. Length will come here. Here also take LCM. This is r1 r2 and it has become r2 minus r1. So you will see that this r2 minus r1 terms get cancelled completely, right? So the final answer that we are getting is resistance is equal to resistivity length by pi r1 r2. This you need to remember. Okay, this result you have to remember. So resistance of a wire whose radius is changing, right? Like this, changing means it's a linear change is happening because the slope tan theta is constant. Okay, if non-linear change is there, then it is a difficult thing. For example, suppose if these are the what non-linear change is happening, no? This we cannot think about it. This is difficult. They must give the equation of this graph. If they give equation, then we can try to do like the same way dy by dx we can calculate and we can think. Here dy by dx is tan theta constant because it's a straight line, right? But in case of a non-linear graph, slope will also change, right? So if we know function, we can do that. It is a little complicated. We can think about that later. But now we got for this uniformly area changing, and this is the resistance of that. Okay. So resistance is resistivity length by area, but area is written as pi R1 R2. If R1 R2 become equal, then it will become a uniform wire. Both radius become same means pi R square means it is a uniform wire. So this we are going to use now. So remember this formula will become resistivity length by area pi R1 R2. R1 R2 are the radius of the ends. Okay. So now let us write this portion resistance. Suppose this resistance radius of this is small r, which you do not know, but this radius r1 you know, that radius r2 you know. Let us write resistivity into length by pi. Here this r1 r2 r1 r you will take, r1 into r you will take, and this wire resistance is resistivity length. Length is how much? I think length you need to give. This length is x, let us say, and this is 100 minus x. Again the same way, 100 minus x and x. So this length you have to take as x, and here it will be again 100 minus x, 100 minus x, and pi here product of the radius is r into r2, r into r2. So when you take the ratio of this, what is the ratio of this? AJ by RJB. So length ratio will definitely come, but another ratio is going to come. R will get cancelled. You will get this as, this ratio will definitely come, and you will also get as R2 by R1. Correct? Extra factor is coming here, R2 by R1, which was not there in the previous case because wire was uniform. Now because non-uniform wire is there, this factor extra will come. So again at null, x is nothing but null deflection length. Null deflection length you are studying. So again you are going to apply balance Wheatstone bridge. The condition is that R1 by R2 is equal to RAJ by RJB. So now you substitute. So R1 become R2 times this ratio. This ratio you have already got, x by 100 minus x into R2 by R1. This is the formula for this type of, this is a case where wire can change, right? Okay, next. So this is over. Meter bridge is over. I think potentiometer is not there for need. So let us leave that potentiometer. So last topic was this. What else is there? Sometimes some ind corrections they will ask. Ind correction. What is in? That is a practical related, practical physics related topic. But let's just understand what is ind correction. Suppose this is the end of this A and B, and you are connecting this with a battery of voltage. Now when you are having a wire and you want to join this circuit, this resistance R1 and this resistance R2, but the thing is that it is very difficult to join this at the end. So in practically end means this last end, how will you join it, right? So sometime in the lab when you are joining, it may join somewhere here, somewhere here it will be joined, and similarly this also it will join here. This is called end correction. So this distance that you are getting, extra distance, this let us say E1 and this distance E2, that is called end corrections. Okay, again you will be doing the same thing, galvanometer will be there and you will be taking this point. So what happens is that instead of taking uh, actual length, you have to consider this point, right? This point should be actual, and let's say this point is a dash, this point is b dash. So you are taking a dash and b dash actual point, but during calculation you may be thinking that a and b I am taking resistance. That's the problem happens. So what will happen is that because of this, error will happen. Error will happen. So so in this case, this end corrections can be done. Okay. So instead of aj, you have to take a dash j, and instead of jb, you have to take jb dash. So instead of aj, you should take a dash j. Instead of taking um, instead of taking jb, you should take j dash b, because connection is made here. Connection is made at b dash and connection is made at a dash. So these are end corrections. Okay. So definitely measurement, when you are doing, you may be measuring, and you will be also measuring from a dash only. So suppose this length you are calculating as x. So from where are we calculating that? Are we calculating from here, or are we calculating from here, from the end? Might be you are calculating from the end. This is x. Okay. And then this is 100 minus x. So now what you need to do is that this actual distance, you have to take this as x minus e1, because it is extra e1 is there. Similarly here, you need to take this distance as, in correction you have to subtract from 100 minus x. This distance become 100 minus x minus e2. Okay. That's what changes will happen. So the ratio of resistances which we are calculating as R1 by R2, this ratio will be actually or correctly written as x minus C1, x minus C1 divided by 100 minus x minus E2. This is what the change in formula will happen. So E1, E2 are end corrections. They will give you in the questions. E1, E2 are end corrections. So from this side, E1 is correction, E2 is correction from this side. Just little bit change will happen in that. Okay. So R1 is suppose unknown resistance, so R1 will be calculated as R2 into x minus C1 by 100 minus x minus C2. That's how we can solve problem. Okay, so this topic is over. Now I think RC circuits are special topics in that. RC circuit, let us take charging discharging circuits. Okay, with this we are going to wind up this. RC charging circuit. Charging circuit. Suppose that there is a capacitor and there is a resistor, and this is connected with a battery voltage V, and there is a switch like this. So this switch is turned on at time 0. At time 0, you turn the switch on. So what happens is that initially there was no charge in the capacitor, so but gradually current will start flowing, so charge will develop. So time 0, the charge on the capacitor is 0, and as some time happens, some charge will develop here, and this charge will increase. So let us now apply. So here positive charge, let us say plus q minus q, and current is going. Some current, if you want, you can write a small I. Some instantaneous current is flowing in this circuit. Now apply Kirchhoff's loop rule, KVL. So you go from here to here, change of potential is minus, so minus negative Q by V, Q by C, change of potential. In the direction of current, minus IR, minus IR. Then across battery -2 plus V is equal to 0. So this is the KVL we have applied. Now once we applied KVL, we want to find out how charge is changing or how current is changing. So from here we can write IR is equal to V minus Q by C, and I becomes, um, if you want you can keep it as it is, but I should be written as dq by dt. I is written as dq by dt. So R times this is V minus Q by C. Now dq divided by V minus Q by C will be written like this, and dt divided by R will be brought this side. Okay, so after you do this, now you are going to integrate this. So time 0 to some time t, charge initially 0 to some charge q. Now you integrate this and try to solve. So let us integrate. So you know this is 1 by linear form is ln will come ln V minus Q by C, and coefficient of Q minus 1 by C will get divided here. It is going from 0 to Q, and right side it is just T T by R. So what do you get finally? Upper limit minus lower limit you can do. Upper limit when you put, it is V minus Q by C. Lower limit is just V, and this side becomes minus T by RC. So then you take power, and here it will become 1 minus Q by CV is e per power minus T by RC. So Q becomes CV 1 minus e per power minus T by RC. This is how the charge is changing in this capacitor. So charge Q is equal to CV. CV is like maximum charge, 1 minus e per power minus T by RC. Okay, so you can put time anytime you put, and you can calculate. Suppose time 0 means 1 minus 1 will become 0, so total charge is 0 on capacitor. And when you take very long time, so e per power minus this means minus infinity, e per power minus infinity 0, e per power minus infinity 0 means this will become CV. So here you have to note important thing that, and also before doing anything else, current also you calculate. Current is dq by dt. Calculate current. When you differentiate, you will get CV. One differentiation 0, here minus will come. E per power minus T by RC will come, and also internal differentiation you have to do, that is minus 1 by RC. So from here minus minus plus will become, current will become, CC get cancelled, V by R e per power minus T by RC. This is the current. So this equation of current and charge you have to remember. So charge is equal to CV 1 minus e per power minus T by RC, and current is V by R e per power minus T by RC. Okay, and you can draw the graph of how current and charge changes. So suppose if I draw Q versus T graph. Initially there was no charge, and there is a maximum charge CV that happens at very long time. So the graph is going to be like this. Okay, it's an exponential graph. That graph will become maximum charge CV. This will maximum will happen when time becomes infinity, very long. So when time become infinity, charge become maximum. Okay, charge become maximum. Okay, similarly current graph also you can draw the current graph, I versus T. Time 0 current is maximum. Note that time 0 current is maximum. This maximum current is V by R. After that what happens, time increases, infinity means current becomes 0. So this current is decreasing here. At infinity it will become 0. Time infinity, current will become 0. So this is interesting thing to note that time 0 current is maximum, that maximum value is V by R. And when time is very, very long, infinity, current becomes zero. So whenever current is maximum, this is called short circuit. This is called short circuit. And whenever current is zero means it is called open circuit. Okay. So these two concept is very important. Short circuit and open circuit concept. Okay. I will explain how this will be applied in these problems. Suppose for example, if there is a capacitor and there is a resistor R, let us take this is 10 ohm and capacitance is 10 microfarad, and you have connected to a battery of voltage, some voltage 100 volt. Okay, and let us consider there is one more circuit you take, means one more branch you take, one more branch. Let us take this is 20 ohm, and now this is a battery. There is a switch here like this. Okay, right, let's take this question. Battery has 100 volt. So 120 ohm is there, 10 ohm is connected in series with the capacitor. So let us say you switch on. Let us say you switch on. So time 0 on. Time 0 you switch on means what will happen is that this capacitor maximum current will go in the capacitor. That you have to note. Okay. So that means this will behave like a short circuit. Okay. Maximum current goes in this means what? Maximum current means short circuit means you can remove this capacitor and you can make just remove the capacitor and make the upper resistance and lower resistance. That's all. That is meant by short circuit. You have to understand this. This is 20 ohm and 10 ohm. Are you understanding that? So short circuit means the capacitor which was there is gone now. It has become short circuit. Okay. This happens only at time 0. Okay. This happens only at time 0. So time 0, this will be the case. Now they may ask you to calculate the current here or here. They may ask. Now you know, no? This is parallel combination, right? Both are having same 100 volt. So current in the upper and current in lower you can calculate because voltage is same, resistances are different. So current is I equal to V by R. So 100 by 20. 100 by 20 means 5 ampere will go here. Here 100 by 10. 100 by 10 means 10 ampere will go here. Total current will be 15 ampere. Correct. So very simple like this. This happen only at time 0. But suppose they say that for long time. So long time is time infinity you take. What will happen in that case? In that case, this will become open circuit means there won't be any current. Open circuit means what? Let's understand. Open means it is like this. This is 20 ohm, this is 10 ohm. This is open circuit. Okay. This one is open circuit. And this one is closed circuit. Sorry, not short circuit. Closed means circuit is always closed. Short circuit. Okay, so when open circuit means no current can go because circuit has broken now. Circuit break. So current will only go in this branch then. So this current, whatever it is, so total current voltage by this, so the 5 ampere only will flow. There is no, so total current is 5 ampere only. There is no current in the upper branch. Clear? That's what happen in any circuit whenever it comes now. Whichever branch contains capacitor, you have to treat like that. Time 0, you have to short circuit. Time infinity, you have to break that. Okay. This is what it is. Done. And this is a charging circuit, and discharging is just the opposite. So I will write the formula for discharging. Nothing is that. Discharging just the reverse case. So discharging RC circuit means what? So now let us say capacitor is already charged, plus Q and minus Q, and you are connecting this with a resistor R, and there is a switch. Now what happen is that you connect this switch. Switch is open, means switch is on at time 0. So capacitor is already having charge, some charge is there. Now when you connect this, then charge will discharge, charge will flow to the resistance. So in this case current will be flowing in this way. So I will write the formula directly. You can solve again like Kirchhoff's law. So Q is equal to capital Q e per power minus t by RC. This is how charge will decrease. Okay, and current you can calculate, differentiate that, right? So if you differentiate here, so current will be how much? You differentiate that, dq by dt you do, so you will get q comes out e per power, this is e per power that only, into 1 minus 1 by RC. So here you will see that this is what it current I comes as q by RC. Minus sign is coming, minus means it is decreasing, minus means charge is decreasing. Or here also you can put a minus sign here, because charge is decreasing, so I is minus dq by dt, so there is extra minus, minus minus will become plus. Okay, so better use that, you can write plus 1. So current will be given by this. If you draw the q versus t graph here, so initially charge is maximum, here charge will be capital Q, and this charge will be decreasing like this. Similarly, if current I versus t graph if I plot, so at time 0 current is again maximum, and current is also going to be decreasing like this. Okay, maximum current is Q by RC. That's all. And note here that this factor RC is called time constant. RC is called tau. This is called time constant. Time constant. This factor RC is called time constant. Clear? Here also you can note its behavior. So at time 0, if you take, current is maximum. Time 0, current is maximum. And time infinity, anyway current becomes 0. Okay. So generally questions don't come on this. So time 0 they may ask, it will become like a short circuit. Okay. They may ask charge and current calculation. Clear? So with this we wind up this chapter. Now you have to work out problems. Moving coil galvanometer is in next chapter, magnetism. Okay. So do work the questions in worksheet already I have sent. Okay. Then next class doubts I will take. Fine. What? Could you repeat? Already this concept is sufficient, whatever we have discussed this concept, and you revise the formulas, right? You take half an hour to revise all this. You are also making notes, you have class notes, right? So that revise in half an hour, after that you start working problems. Okay, fine. So next class onward we'll discuss problems. One class we need to discuss problem magnetism also, we have to start them. Okay, fine. Okay, bye bye.